But more interestingly, we have a guest lecture today from Wen's son. So Wen's currently a professor at Cornell, soon to be Cornell Tech, and before that he did his PhD here at CMU, actually with Drew. I frequently describe myself as the sort of dollar store knockoff of Wen, and I think the paper Wen will be presenting today is a particularly good example of this. So the backstory behind this paper is that Wen, Drew, and I had a meeting. And a few hours afterwards, Wen sent me a Slack message where he was like, "Hey, I came up with a new algorithm. Can you take a look?" And I remember being like, wow, I have no idea how you took that particularly vibey discussion and turned it into like a concrete implementable algorithm that achieves state-of-the-art performance in like a single day. At this point, I think the main value I provide to Wen is that I am better at coming up with algorithm names, and I spend enough time on Twitter that I can kind of keep him in the loop on interesting memes like vibe coding and the like. So I'm very glad he continues to choose to work with me and be very generous in many ways. Anyhow, we're very lucky to have Wen speaking with us today on what I think are some of the most interesting, practical, and scalable algorithms for getting RLHF to work in practice. So please take it away, Wen. Thank you.
All right, thank you. Can you guys hear me well?
Yes.
All right, okay, so let's get started. I'm going to tell you an algorithm called a REBEL, in short, regressing relative reward-based RL. Okay, maybe let's do a quick recap. I think you guys covered some of the basics about RLHF and DPL, right? So in those settings, we typically just focus on the KO regularized RL objective. So we're trying to maximize some reward function. And at the same time, we're trying to say that let's stay close to pi ref, right? And if you solve this optimization problem, you will see that the optimal policy has this format, which is the product of the policy pi ref that you're trying to stay close to, and then exponential of the reward on that particular response type. This means that this form allows you to sort of trade the balance between stay closing to pi ref and also optimize the reward. And DPO basically took this idea, right? It basically says that, okay, let's take the closed form solution that we had from the previous slide. Let's just do a reparameterization. Let's just to represent the reward by the policy. And more importantly, they say that let's represent the reward difference using the policy, right? So here you're basically going to model the reward difference using the difference of the log of these two policy ratios. Right, so that's what they meant in the paper, that your language model is a secret reward model. So this whole thing is basically trying to model Rx tau minus Rx tau prime. Right? And then we know that there is some model called a Brett-Taylor model, and we can design maximum likelihood estimation objective function using Brett-Taylor model. And what we do is just plug in this alternative representation of the reward difference into the maximum likelihood estimation loss, and that gives you this DPO objective function. Right, and the DPO basically just take a offline data set that consists of prompt, two responses, and a label Z. Let's say Z is -101, right? And take this data set as input and just optimize this objective function, and then you get a policy direct. Okay. And it works well. It's a pretty simple method, right? You doesn't feel like you're doing any RL anymore, so it just feels like you're doing supervised learning. You're trying to increase the likelihood of your policy on a chosen trajectory, and at the same time trying to decrease the likelihood of your policy on the rejected trajectory. That makes a lot of sense, right? Okay, but in practice, people don't stop at the DPO, right? After DPO, if you look at those technical reports from these, big labs, and when they do RHF post-training, they don't stop at DPL. So they do DPL first, and then they actually still going to use the thing that you learned before. They're still going to do this reward model plus online RL, particularly they use PPL, for instance, to further post-train the model, right? And you often can see a performance gap. And the intuition behind this gap is that when for the problems where there are evaluation and generation gap, meaning that evaluation can be much easier than generation, then this reward modeling plus PPO or online RL approach can actually win. Right. So first of all, DPO only uses finite data. So you give DPO the finite number of pairs of responses. And DPO can only take advantage of that, right? And the DPO in high level basically take that finite data as input, does a bunch of finite number of gradient descents on the parameters of the generator directly, and then output the generator. right? So this means that in high level, DPO is a generative modeling algorithm. If you remember the concept of discriminative learning versus generative learning from Intro to ML, right? So DPO is a generative modeling algorithm. It takes the data as the input to do a bunch of finite computation and outputs a generative model directly. It doesn't do discriminative learning. But if you look at the reward modeling plus the online RL approach, the reward modeling part is discriminative learning, right? It doesn't try to learn how to generate. It's just trying to learn how to label two responses. For tasks where discriminative learning is much easier than generative modeling, then this reward modeling plus PPO approach can win, right? You can trust your reward model. Maybe your reward model can actually just take this finite number of data points and give you a much better verifier that can tell you which response is better than the other, right? Even though the reward model itself doesn't know how to generate. And if you trust your reward model, if your reward model can generalize well, then you can take advantage of online RL, right? You can actually use PPO to actually optimize those unseen prompts that don't have human labels. And you can also generate synthetic data using a policy on the fly and label them using your reward model and optimizing your policy. So in summary, if you trust that your problem has actually this verifier and a generation gap, then reward modeling plus PPO can do better. Or in general, reward model plus online RL can do better than DPO, right? DPO, pretty much can only take advantage of the finite data that you have. Okay, another benefit which I think is a real benefit, is that reward modeling is actually a very active research area, right? And if you look at online, like Hugging Face, they have a reward bench. They have a reward benchmark there. And every day, people try whatever new approach that they come up and train a reward model on some of their own data set, maybe, and they post that reward model on this benchmark, right? And if you want to do RHF, maybe you don't even need to train a reward model from whatever the small size of preference data that you got, right? You can actually go to this benchmark and pick the one that, works for your application, or just pick the state-of-art model from this benchmark, right? And then you can do online RL on top of it, right? You don't need to worry about how the reward model is trained, how the reward model is what kind of data they use to train the reward model. All you need to do is just take the best reward model or the reward model that satisfies your application and run online RL on top of that, right? Okay, so what we're trying to address today is that this reward modeling plus PPO is good. PPO is an online RL algorithm that can take advantage of online fresh synthetic data. But PPO is kind of expensive, right? If you think about how to do PPO for language modeling, at any time during the optimization, you kind of have to maintain at least 4 big models, right? So you have your pi, and you have your pi ref, right? And you have your reward model, R, okay? And you also have the value function, V, right? Don't forget about the value function, right? PPO trains value function and they use value function together with something called generative advantage estimation to compute advantages for every tokens and then to update, right? So if you have a lot of compute resources, and if you're comfortable about tuning hyperparameters for PPO, then this might be okay, right? But if you're not comfortable about tuning these crazy amount of hyperparameters for PPO, or you don't have too much computation resources, maybe you just can't take advantage of PPO. You can't do PPO too much, right? And what we are trying to do here is to say if we can develop a new RL algorithm that is more efficient in terms of computation and memory, maybe GPU memory, maybe at the same time as effective as PPO, or maybe even better, even more effective than PPO. And this is the 3 things that we're going to go through today. I'm going to do a quick recap on mirror descent. I think you guys covered mirror descent in great detail, right? You guys actually did the proof probably for mirror descent, and I didn't do this in my class at Cornell. But I'm just going to do a quick recap on mirror descent because the algorithm that I'm going to tell you in the second part of today's lecture, this rebel, is motivated from the principles behind mirror descent. And finally, I'm going to tell you some interesting connections to some of the very old algorithms that you learned in this class. Some of the connections were actually surprising when we were working on the paper. And then lastly, I'm going to show you some experiment results. Okay, so mirror descent. let's assume that we are given a reward function, okay, for now. So the reward function could be learned by yourself on your preference data that you collected in some way, or it could be some open source reward model that you got from some benchmark leaderboards, right? So we have some reward model. And what we want to do is to just optimize a language model, optimize a policy pi that maximize the expected reward. That's our goal. All right. And what we can do, how can we optimize this objective function? Well, if your policy pi is parameterized by some parameter theta, say it's a transformer where theta represents, the weights in the transformer, right? You can do gradient descent, right? You can do, let's say, reinforce, right? To optimize the parameter, you can do NPG, right? NPG is not that scalable, but you can do, let's say, PPO, for instance, right? You can use this incremental gradient descent based algorithm to optimize the parameter data. So mirror descent in high level does not directly work at the parameter space, right? It's trying to do everything in the policy space in a more abstract manner. So it basically trying to incrementally update your policy as follows. So let's say given pi t, which is the policy that you have in your hand at this moment, I want to update my policy pi t to pi t plus 1 as follows. Okay. I'm going to solve the following KO regularized objective again. So I want to optimize the reward model that I have. Okay. But at the same time, I basically say that, okay, don't deviate too much from your pi old, right? This is the older policy, the one that I have at hand. That's basically mirror descent is trying to do, right? Conceptually, gradient descent is sort of doing similar things, right? Gradient descent is essentially saying, let's optimize whatever the reward or the objective function that I have, but at the same time, don't move too far away from where you were. And mirror descent is just using a very specific divergence, which is KO divergence here, to model the distance between the policy that you're trying to optimize and the pi old that you have. And this should remind you some of the old algorithms that you learned, right? Let's see, NPG, natural policy gradient. NPG is essentially using KO divergence, but approximating the KO divergence using its second order Taylor expansion. And this should also remind you the logic behind PPO's clipping objective, right? PPO basically say that, okay, computing the Hessian of the KO divergence like TRPO or NPG doing is too expensive. Let me just heuristically approximate that divergence using sort of the clipping objective. Okay, so let's move on. So if I use the same derivation that we had for the KO regularized RO objective, right, we can immediately arrive at the optimal solution for the new policy pi t plus 1, the analytical update formulation for the new policy pi t plus 1. Right, this basically looks like the product of the pi old, the previous policy that you're trying to stay close to, and the exponential of the reward. Right, so the same format as the KO regularized RO objective. Okay, so this is the analytical form for the mirror descent update. This all looks good, right? And maybe on papers, on papers, we can keep writing this, right? We can do pi t plus 2 proportional to pi t plus 1 times exp of r over beta. And we can do pi t plus 3 proportional to pi t plus 2 exponential of r over beta, right? We can keep doing this, simple. But one question that I want you to think about this is, can we actually easily implement this procedure in our computer, for instance? Right? This gives you a very nice analytical form. If you think about this a little bit, right? It's not super easy to convert this analytical form into something in our computer, right? If you think about, let's say pi t is, let's say this is a language model, okay? Let's see reward function is also another neural network, let's say transformer, okay? So you have two transformers, and you're looking at the product of one transformer and exponential on the other, the output of another transformer. I don't know how to represent their product, right? Using, let's say, a third transformer. So we have very nice analytical form, but we don't know how to turn this analytical form into something that is implementable, something that we can use to generate tokens. Okay. But for now, maybe let's ignore about the implementation issue a little bit. I will tell you the Rebel algorithm, which is basically trying to address this problem, right? And allow you to actually mimic mirror descent while at the same time directly working on a parameterized language model or parameterized policy. But let's ignore about the implementation issue for a second. Let's say that we are happy about, just doing everything in this analytical ideal form. So mirror descent in theory has a very good convergence rate, right? So particularly, I think you learned that in the class already. After capital T many iterations, if you keep doing pi t plus 1 proportional to pi t times exp of r over beta, right? If you keep doing this for capital T many rounds, then you're guaranteed to find a policy pi hat such that the performance gap between your policy and the optimal policy in terms of maximizing the reward shrinks in the rate of 1 over capital T. Right? That's pretty good. 1 over T is a pretty fast convergence rate. Well, this is the slides that I use for my class, so I guess you saw the proof. All right. Cool. Okay, so it's a very good algorithm. Conceptually, it's a very good algorithm. If you're willing to do this analytical closed form update, then we are good, right? Okay, but the problem is that we can't really do this, right? You kind of have to implement this guy in your computer in some parameterized, form so that it can generate tokens, right? And we can't just, be happy about just the analytical form of the mirror descent. Okay, so that leads to the second part of today's lecture. Let's do the reparameterization trick again, and let's talk about the Rebel algorithm. Okay, so we're going to start from the analytical update form from the mirror descent procedure. Okay, so here, instead of writing things in terms of proportional, I'm using the exact equality. Okay, and then I'm going to divide this by a normalization constant, Zx. Right, so Dx is just equals to the expectation of tau from pi t given x. Okay, exp of rx tau over beta. Okay, so this is just a normalization constant so that now sum over tau pi t plus 1, tau given x is equal to 1. Okay, that's just trying to make sure this is a distribution, meaning that you sum over all possible taus, then the sum is equal to 1. So it's a valid distribution. That's it. Not super important. Okay, so let's do the reparameterization trick. I'm just going to add log on both sides of this expression. Okay, and then I'm going to pull the reward function out, like what we did in DPO. And this is what we're going to get. Okay, I basically arrive at this relationship between the reward and the analytical form that I would get if I run this mirror descent step. Okay, so this is literally just coming from the mirror descent update. We're almost there, but remember that this term log z is kind of annoying, right? Because z technically depends on the reward. So this is expectation of pi t, then exp of r x tau over beta, right? So this guy depends on reward as well. So z actually depends on reward. So it's not really sort of a reparameterization of reward yet, right? Because if you look at this expression here, on the left-hand side, you have reward, but on the right-hand side, your normalization constant depends on the reward as well. Okay, let's just follow the trick that DPO had, right? So instead of modeling the reward, let's just model the reward difference. Maybe all I care is just the reward difference between tau and tau prime. Okay, I don't really need to learn the exact reward. All I care about is if I can model the reward difference, right? That's good enough. So let's do that, right? So instead of modeling the reward, let's just model the reward difference. So just look at the difference between tau and tau prime measured under the reward R. This is kind of nice because this guy goes away, right? The log z is independent of the response tau, so this just cancels out. Okay, so far it's very similar to DPL. Okay, put this together, we basically obtained the following relationship between the reward model R and the analytical form pi t plus 1 that we would get if you round mirror descent. And this is as follows. For every possible triple x tau tau prime, we will have the following relationship between the reward difference and the ideal policy pi t plus 1 that we would get by running mirror descent in its analytical form. Okay, so left-hand side has to equal to the right-hand side for every x tau tau prime. right? This is just coming from the closed form update of mirror descent. Okay, so yeah, question?
So what's the difference with DPO? Maybe it's exactly the same.
Right, so here, DPO was using PyRef, right? So I guess we're using PyT. We're basically saying that I'm only gonna stay close to the previous policy, right? Not PyRef at this point. I mean, the derivation is very similar, right? The motivation is very similar. And we also use the trick of modeling the reward difference so that we can cancel out the partition function.
Right.
Okay. Okay, so this models the relationship between the reward and this ideal analytical form, right? But as I said, we can't just take the analytical form and implement this in our computer. It doesn't work that way, right? This analytical form doesn't give you something that you can generate tokens. So we have to learn this analytical form. We have to approximate that using a parameterized model from which we can sample. And we're going to use this relationship to turn the problem of finding, approximating this analytical pi t plus 1 into an optimization problem. All right, so I'm going to take advantage of this relationship. I'm going to model a optimization problem whose optimal solution will be the analytical pi t plus 1. So let's do the following. I'm going to design a least square regression problem such that pi t plus 1, this analytical form from mirror descent, is one of the minimizers of the least square regression problem. Okay? So the least regression problem is actually pretty simple. This is as follows. I just want to train a regressor that can actually accurately predict the reward difference. Okay, so first thing to notice is that this relationship implies that pi t plus 1 has to be the minimizer of this objective function, right? Because this has to be 0. So 0 is the minimum value you can get for a least square regression problem. So pi t plus 1, this analytical form, has to be the minimizer of this expression. And this has nothing to do with what distribution you're going to use for x tau tau prime, right? Because the relationship holds for every triple x tau tau prime. So this means that you can do any training distribution here. It doesn't matter. Pi t plus 1, the analytical form solution, will be the solution that drives the loss to be 0. Right? And in practice, when we design an algorithm, we're going to replace the expectation, the training distribution, using the current policy pi t that you have at hand. Meaning that we're going to sample the prompt from the prompt distribution, and then we're going to sample 2 responses independently from the current policy pi t you have. Okay. And this is the relative reward, which is trying to model how much better tau is compared to tau prime, or how much worse tau is compared to tau prime. All right, so yeah, go ahead.
What if you have distribution that's not identifiable, like, it's not the unique solution or something?
Yeah, this might not be the unique solution, right? Given the distribution. But under some assumptions of the coverage of the distribution, we don't need to exactly find this minimizer. Any solution that minimizes this objective function well should work under some assumptions of the training distribution's coverage.
Okay.
Okay, so let's move on. Let's now put everything together into an runnable and implementable algorithm. All right. So given pi t, the policy that you have, the language model you have, we're going to compute pi t plus 1 via the following least square regression problem. Okay. So we're just going to search for a new policy pi that minimizes the following regression problem. This is our training data, training distribution. Okay, so you sample x from prompt distribution, you sample tau tau prime independently from pi t. And then this is your regression target, right? You're trying to predict the reward difference between tau and tau prime, and you're going to treat this whole big thing as your regressor. Right? So this is pretty much a least square regression problem that you learned in the intro to ML, right? I'm taking some neural nets and model this as a regressor, and I'm trying to predict a well-defined target, which is the reward difference in this case. Okay. We can approximately solve this least square regression problem, get pi t plus 1, and then repeat. We can repeat this for multiple iterations until we get a policy that performs well on the validation set, for instance.
So it's still an online algorithm because you have to draw from pi t.
Correct. Yeah. So this is an online. This is in some sense some sort of on-policy algorithm, right? We're trying to draw samples from the latest policy, but there is a lot of freedom in terms of designing this distribution, right? For instance, you can do hybrid, right? You can draw tau from pi t, and you can draw tau prime from best of n of pi t, right? So this is actually something that we did. So we draw tau from pi t, we draw tau prime from the best of n of pi t. Right, you can do this, right? Because you have a reward function. Rx tau. You do best of n using your reward function R. You can also take advantage of an offline data, right? So if you have some good human demonstrations, then maybe tau prime can be one of the human demonstration for the prompt X. Right, so there's some flexibility here, but for now we're just going to focus on policy sampling.
Cool.
All right. So I guess this is the algorithm, Rebel. Let's just spend some time talking about what's the difference between DPO, Rebel, and PPO, right? So first of all, DPO, right? It uses this finite preference data. Okay, you can't really scale up that data set really well, right? Because it requires human labels. So we can't really, scale up the human labeled data set to something like the internet scale data set, right? This seems impossible. People start using big language models as a human to label their data, but still that's expensive. It's harder to scale up that data set size. And DPO is offline. Okay? It just uses the offline data and doesn't try to leverage any of the synthetic online fresh data. Okay, PPO, it uses the same finite data to train a reward model, and then it just trusts the reward model and it do a bunch of online RL optimization. RL, right? And PPO generates synthetic data and can also optimize the policy on unseen prompts, right? Prompts where you don't have human labels, for instance. Right? And I will say Rebel is just something that sits between 1 and 2, right? Unlike DPO, Rebel also uses online fresh data, okay? But unlike PPO, Rebel does not need a value network. Right. So very similar to DPO, it operates at the trajectory level. It doesn't operate at the token level. So we don't need to worry about training a value network, for instance. Okay. In practice, that makes a big difference. Rebel is actually way more efficient than PPO in terms of computation and in terms of GPU memory. Okay. So almost as efficient as DPO in terms of memory and in not memory actually in terms of computation efficiency. Okay, so let's move on. I'm going to tell you a little bit about the connections of Rebel to some of the older algorithms that we learned so far. In order to do that, let's be specific, right? Let's, instead of staying at this abstract policy space, let's just talk about parameterized policy, pi theta. Right? Theta is your parameter, okay? So the parameter that you want to do gradient descent on. I'd convert the least square regression problem to the following expression, which is basically the same, but I'm just trying to search the parameters now, right? This is a differentiable policy, right? And this is my transformer, for instance. I want to optimize the parameters of transformers to minimize this least square regression problem, all right? And as I said, we cannot exactly solve this, right? In practice, what we do, we take this data set and we take this transformer pi theta and we compute the gradient of this objective function and we do a bunch of gradient descent, right? So we can only hope to approximately solve that. Okay, how to solve it exactly? Now, what are we trying to investigate here is that what happens if we just solve it approximating, right? And more concretely, what happens if we perform the following two things? First, what if we're just happy about minimizing this objective function by just one step of gradient descent on the parameter theta? Okay, that's not a very good optimizer. You know, one step gradient descent can't really minimize the objective function too well. But let's say we are happy about that. Let's say we just want to do one step gradient descent on the objective function and move on to the next iteration. What happens? Okay. Second, let's say we do something between, you know, the first order optimization gradient descent and the second order optimization Newton's method. Let's do something like Gauss-Newton. And we're just going to do one step Gauss-Newton. Okay, let's say we are happy about, you know, just minimizing the least square regression objective function by one step Gauss-Newton on the parameter and then move on. What happens? Okay, so let's check out the first thing. What happens if we do one step gradient descent? Okay, so this is my loss function L theta, right? This is just a loss function that takes parameter theta as input and it gives me a scalar. And I can just do one step gradient descent starting from theta t where I were and do one step gradient descent to minimize the objective function, right? And let's see what the gradient look like in this case. Right? This whole thing looks kind of complicated, right? But what's the gradient? What's the gradient of this loss function measured at theta t? Okay. Okay, so let me just do this for you. Let's just focus on a given x tau triple, okay? Don't worry about the expectation. You can compute the gradient and add the expectation back, but let's just do gradient on x tau prime, okay? This is square loss, right? So I have to do one step chain rule. I have to take the derivative of the square loss and then go inside the square loss, compute the gradient of the theta. Okay, so gradient theta L theta is just first do the derivative of the square loss, right? So this is beta log pi theta tau x theta t tau x minus log of prime. Okay, minus rx tau minus rx tau prime, right? Okay, so I'm just taking care of the derivative of the square loss, and then I go inside the square, compute the gradient for the parameter theta, right? So this just, but if you see this guy is independent of theta, it's just theta t, right? It's independent of the parameter theta that I'm trying to optimize. This guy is independent of the theta. So what left is just these two terms, right? They depend on theta. So what I left here is just multiply this with beta gradient log pi theta tau given x minus beta times gradient log pi theta tau prime given x. Yep, okay. That's a gradient, okay? Now what happens if I set theta to be equal to theta t, right? I want to compute the gradient on the places where I were, right? Which is theta t. Then I do gradient descent, right? It's just plugging theta t into the gradient expression. Now I claim that if you do this, right, this guy goes away, right? Because the ratio of the two policies is going to be 1 if you replace theta by theta t. And this guy goes away too, right? So what I left is r is negative r x tau minus r x tau prime multiply. I'm going to pull the beta out here. Gradient log pi theta tau given x minus gradient log pi theta tau prime, right? T here. Okay, good. Right, at this point, this should remind you of something like a policy gradient, a reinforced format, right? Because I can rearrange in term a little bit. I can write this as, you know, negative beta times gradient log pi theta t tau given x multiply rx tau minus rx tau prime, right? Minus another term, pi theta t tau prime given x rx tau prime minus rx tau. Oh. Okay. right? So that's basically what I have. If you look at each term, you just look at this term, right? This is just to reinforce, right? And even better, this is reinforced with variance reduction. Okay, because tau prime is independent of tau, right? So this tau prime serves as a variance reduction trick. If you heard about something called R rule, which is reinforced with leave one out, this gradient, this green part is actually R rule with K equal to 2, right? Meaning it's sampling two independent responses from this given CM problem X, and then use one of them as a variance reduction trick. Okay. So the second term is just a symmetric term. You just switch the role of tau to tau prime, right? It's just another gradient. So if you just do one-step gradient descent on this objective function, you basically recover something like R loop, reinforced with leave one out. All right, so that's pretty good. You know, by doing this, regressing to the relative reward, we kind of sort of recover reinforced with leave one out, and we get some benefit of variance reduction as well. So let's continue. Okay, so let's see we move beyond first order optimization. Let's see, I want to solve this least square regression minimization using one-step Gauss-Newton. Okay, you may heard about Newton's methods, but you probably don't know what is Gauss-Newton. Okay, let me explain this to you. So this applies to square laws in this case. Okay, what Gauss-Newton gonna do is basically go inside the square laws, replace the nonlinear part inside the square laws by its first order Taylor expansion. Okay, so in this case, this part is nonlinear with respect to theta, right? So pi theta could be very complicated transformers. So the dependence of this term inside this green circle is nonlinear with respect to the parameter, non-convex, right? So what Gauss-Newton basically says that I don't want to deal with this complicated nonlinear stuff inside the square laws. Let me just approximate this whole thing by its first order Taylor expansion, okay? So basically, I'm taking this nonlinear part and I'm approximating this by its first order Taylor expansion. So this is the first order term. Okay, so this is just a gradient, right? Okay, you may wonder where is the zeroth order term, okay? So you can verify that the zeroth order term is actually equal to 0. So that's why I don't write it down here, because it's just 0. And because this is first order Taylor expansion, so I also get rid of, you know, the second order or third order terms, right? Something like this. So I don't worry about the second order term anymore. Okay, so I'm just approximating this nonlinear component inside the square laws by its first order Taylor expansion. Zeroth order term is 0. Second, third order term, we just get rid of that. So all we left is this linear gradient, the first order term. Okay, so now Gauss-Newton is essentially going to plug this back into the square laws, right? Plug the linear component back to the square laws and solve a linear regression problem now. Okay, so let's do this. Let's plug this linear term back into the square laws. I got the following linear regression problem, right? So now this is just nothing but linear regression, something very simple now. Okay, so this is a parameter, right? And what is this? This is a feature of the linear regression, right? And this is the target of the linear regression, okay? So we're literally just doing linear regression with well-defined features and well-defined target. And under some assumptions that the training data's feature spans every direction in the space, then we can really get a closed form solution for the optimal parameter theta, right? For this least square regression problem. And if you do that, if you solve, if you sort of assume that the feature spans every direction and find the optimal solution for this least square regression problem, you will notice that this actually recovers the natural policy gradient updated procedure. Okay, so this actually looks something like, you know, Fisher information matrix times the gradient. The gradient is the policy gradient. The Fisher information matrix is expectation x tau prime from pi t, then gradient, actually just one tau, gradient log pi tau x, right, times the transpose x. Right. So the Fisher information matrix. Okay, so basically I'm saying that the minimizer of the least square regression problem just recovers the natural policy gradient update. Okay.
When?
Yeah.
So we did go over the regression view of MPG,
Yeah,
but we didn't take the differencing term.
right.
Feature is not the difference. Does
Right.
it matter, or do you somewhere use something like realizability?
No, it doesn't really matter too much. I guess the reward difference is going to show up in the gradient. So this gradient term is still going to be the variance reduced gradient instead of just the reinforced gradient, for instance.
Okay.
I don't know if the difference of the feature has any sort of variance reduction effect on the facial information matrix when you use finite number of samples, maybe. But in terms of unbiasedness or whatever, it doesn't really matter.
I see. But somewhere you're kind of using the fact that if I start taking differences of like different examples, or
Right.
take difference of x and take difference of y, the regression target limit in the limit is still the same.
Right. Right.
Okay.
Okay. So we did some experiments on the paper, and so this is, just let me give you some background, and we're trying to train a model to sort of do summarization on the Reddit post. So the task is to take a Reddit post and write a short summary, and we want to do better than, for instance, human written summaries. Okay, so let's start from SFT. So SFT is basically take the model, take the pre-trained model, and just do next token prediction autoregressive style training on the human demonstrations. So some of the data set consists of Reddit posts and a human written summary, right? So you can just take the post as input, conditioning on that, and train your model to autoregressively predict the tokens in the human responses, in the human demonstrations. That's like behavior cloning, right? So it gives you something like, 50-ish% of win rate, which kind of makes sense, right? If you do behavior cloning reasonably well, then your trained model roughly do as good as the human demonstrator. Okay, so that's reasonable. And you can do DPO on the preference data set. So that data set also consists of thousands of human labeled preference data. So you given a prompt, which is a Reddit post, there are two responses, tau and tau prime, and there's a human label indicating which one is better. Okay, so you can just take that part of the data set and run DPO on it. Okay, so DPO significantly boosts the performance of SFT. Okay, so this means that training things on the preference data is actually being pretty helpful compared to just mimicking, human demonstrations. So 68% win rate means that at least based on, the GPT-4 perspective, DPO model is actually doing reasonably better than human demonstrators. Okay, so this is doing better than human demonstrators. Okay, but if you compare DPO's performance to these online RL algorithms, right, reinforce, PPO, RLU, and Rebel, you will see that online RL plus reward model, right, the reward model is trained under the same preference data that we use to train DPO, is often better than DPO. Okay? Actually, by a margin, if you look at PPO's performance and RLU with k equal to 4's performance. Okay, this is the first message. So the second message is that if you compare Rebel to PPO and RLU, k equal to 2 and k equal to 4, right? Rebel is, maybe in par or slightly better than these baselines. We actually run multiple seeds and take average, right? If you look at the previous work that we cited here, they just did one seed. I don't know how they picked the seed, but they just did one seed and report numbers. So we did something pretty, slightly better. We take multiple random seeds, take an average, compute the STD, right? So we are slightly better than these baselines, PPO and RLU. But remember, comparing to PPO, Rebel is much, much more computation and memory efficient, right? It runs much, much faster than PPO, right? That's probably why, even for these AI startups, these companies, they cannot really run PPO with multiple seeds and a take average, right? So, but that's just what it is. And compared to RLU with k equal to 2, Rebel is still much better. They have similar computation. And compare RLU equal to k equal to 4, Rebel is still slightly better, but RLU with k equal to 4 is actually way more computation intensive, because when the model gets larger and larger, inference generating responses is actually going to take a lot of time now. Okay, so generating 4 responses or maybe even 8 responses per question gonna take you a lot of time to do that when the model is really long.
And some questions?
Yeah.
Yes, sorry, this is super interesting. So SFT is just doing SFT on the preferred completion?
No, I think for this data set, there is like X and tau pair, where tau is from human generation, human depth.
Okay, there's a human reference summary.
So this is just a behavior cloning on that data set.
And I guess you went over some variations. Is it with Bell or Rebel? Like, sometime your collaborator called it Rebel, and I'm biased. Anyway, but there's also potentially practical things you have to do. Like, do you have to deal with these log ratio being super big? Like, do you have to do some kind of clip? No, like.
No, we don't do any clipping here. I think one benefit of Rebel is that we are using square loss. Okay, square loss turns out to be much better than the logistic loss, which you use in DPL.
I see.
It's less over optimization compared to logistic loss.
So all you do is generate a pair of completion for every prompt?
Yep.
And do regression on it?
Correct.
And
repeat this for 3 or 5 iterations. That's it.
And RLU is just like double the generation, but do one step gradient.
Correct.
I see. But
well,
K
equal to 4 doubles the generation.
I see. Is K equal to 4 like much more than? I guess there's a gap between RLU with K equals to 2, and then K equals 4, and then Rebel or Rebel.
Right.
Like, which one is like more expensive?
RLU K equal to 4, right? Is more expensive.
I see. So because doubling the generation is much more than like running multiple step back prop.
I mean, for 7 billion size model, maybe it's okay. Like if your implementation is efficient enough, if you use this fast inference engine, right, like VLLM, you can do that. But when the model gets larger and larger, it just gets slower and slower. You're actually going to spend a lot of time doing generation instead of optimization. And in these cases, optimizing the parameter once you generate the data is actually pretty fast.
I see.
We actually spend a lot of time on generation.
Got it. So, and maybe the takeaway is that these stepwise regression problems are kind of easy to solve. Hyperparameter are not crazy.
Not that crazy, right?
Okay, cool.
And I mean, I think hyperparameters is not that sensitive. I think the benefit of this is the square loss gives us some benefit compared to logistic regression loss. And yeah.
It's interesting that the ratio didn't bother you at all in the square loss.
Yeah. Did you guys find something different? You have to clip it?
Oh, well, I haven't done it myself, but I would expect like if you have really low probability in the denominator, something will blow up sometimes.
Because we're sampling from the denominator though, right?
Oh, I see. Yeah. Okay.
Yeah, I think it's probably because we're doing
It's
on-policy
far
sampling. Yeah.
Yeah. Okay.
Yeah. So we have, in addition to these experiments, we have other larger experiments in the paper, but I'm not going to go through that. And you can also apply this algorithm on fine-tuning image generative models. So we take some diffusion models and we apply Rebel on this as well. And that works pretty well as well. The last thing that I want to mention is, okay, not here. Oh, is the OpenAI Gem environment. So so far we mostly focusing on how to apply these RLHF algorithms to language model, right? But you can apply these things like Rebel, for instance, to the OpenAI Gem environment. So in this example, what I did is that I take this swimmer simulator from OpenAI Gem. I collected a pair of trajectories using some high-ref, some checkpoint that I got by training reinforcement learning algorithms using the ground truth reward. All right, so I just take some mediocre pi-ref and use that to generate pairs of trajectories. And then I just label the pair of trajectories using the ground truth reward, meaning that if trajectory 1 has higher total reward than trajectory 2, I just say trajectory win weight. Trajectory 1 is preferred over trajectory 2 and vice versa. So I just create a data set that consists of, let's see, 5,000 pairs of trajectories and labels. Okay, and now I can do DPO, and I can do reward modeling and Rebel, for instance. Okay, so this is what I got by comparing DPO versus Rebel. Okay, so on this plot, the x-axis is the number of gradient updates, right? Number of the mini batch gradient updates. The y-axis is the reward of the policy. All right, so everything on this side is corresponding optimization on the offline preference data. So this is optimization using the offline data. Okay, so just take the offline data and loop through this offline data using multiple steps of mini batch gradient update. Okay, so everything on the left-hand side of this green bar is optimization on the offline data. Okay, so of course DPO stops here, right? Because I went through the data set once, I just do one epoch, and then I stop. And of course you can keep doing more epochs here, more epochs for DPO, but you will see that the performance drop because DPO gonna overfit it to the training data. Okay, so I just stopped it there. And now for Rebel, everything on the right-hand side of this green bar is going to be optimization using the fresh online rollouts from your policy pipe, right? Because at this point for Rebel, it already did optimization on the offline data. Now you get some good policy. So you pick this policy, you're gonna generate more fresh online trajectories. You're gonna label them using your reward model, and then you're gonna run another round of optimization. You stop somewhere here, for instance, then you generate new fresh data, and we repeat this for 5 times. Okay, so the difference between DPO and Rebel is that Rebel is taking advantage of synthetic online data that is generated on the fly, while DPO basically just loop through the offline data and stop the optimization there. Okay, so as you can see that the performance of Rebel, even in these simple old school Mujoka experiments, they're much better than the DPO, right? DPO performance is pretty much just 10% improvement over the PyRef, while Rebel can get to something like, 25% over PyRef. Okay. Making the performance better beyond 25, 30% seems pretty hard. I guess at that point, the reward model becomes sort of a little bit out of distribution, is not able to actually measure the quality of even better trajectory that well. This is probably related to the out of distribution problem. And if you want to make Rebel work even better, you probably have to spend more time on, training the reward model, getting a diverse data set for training the reward model, and so on and so forth. Okay, so I think that's all I have for today's lecture. I think maybe I went through things a little bit too fast, but I'm having.
Any questions? I've been asking a lot of questions. So what would be like a practitioner recommendation? Like if I have a startup, I don't, should I just use Rebel? Like I should not use PPO, or if I have enough time and patience, maybe PPO is still like better in limit.
I don't know. I don't think PPO actually is really, really better in some sense. We also applied Rebel to some of the math reasoning tasks. It works a little bit better than PPO and GRPO, actually. So I actually don't see really a place where PPO is actually absolutely winning at this point, at least from the experiments that we could try on academia and models. Right? Maybe OpenAI really knows how to get PPO to work, or they have really good infrastructure to train PPO because it's from their, PPO is from them, right? But I mean, DeepSeek clearly didn't use PPO, they just do GRPO, right? But there's also no clear evidence that GRPO is actually better than PPO in some sense.
Right.
Right. So
they're faster, I guess. Both GRPO and
faster, sure, yeah. I don't know. I think, Rebel is definitely worth trying. One of the authors of Rebel, Jonathan Chen, he graduated and he joined Databricks, and apparently now they're using Rebel in their product.
Nice.
He just told me that, their team were pushing really hard for Rebel, and another team were actually skeptical about Rebel, but in their final evaluation, their team beat that other team, so now the other team also does Rebel.
I see. And maybe you guys are already writing all these papers, so like you could potentially bring the same idea to other problems that involve solving some sort of RL subroutine, right? Like maybe you can do IRL with this. Maybe you wrote a paper.
Yeah, I think so. I think you can plug in this into the inverse RL framework if you feel that optimizing at the trajectory level for your problem can work, right? Yeah.
Like maybe actually an interesting online SMT or something.
Yeah. When could you, if you'd like, could you talk a little bit about how we could maybe do things like this in a Q function space?
In the Q function space. Yeah. So I guess maybe let's just use this whiteboard here. I wanted to try this out, but I don't think I get a chance to really try this out. For instance, if I run something like, let's see we do something like software actor critic, right? Let's say we do something like SAC, for instance, right? And if we can train a critic that looks like SA, QPy TSA, for instance, right? Then we can use that to form this Rebel objective function as well. So maybe I can do log pi as, right? Pi e as minus log pi a prime s pi t a prime s beta minus q sa minus q sa prime squared. So I can minimize this least square regression problem to get pi out as well, right? So main of this gives me pi t plus 1. Then I can repeat, right? I haven't get a chance to try this out yet, but seems a pretty reasonable thing to try. Take the SAC implementation, right? Get rid of their policy optimization, actor optimization procedure, replace their procedure by this least square regression procedure, and see how it goes. Business.
If you actually wanted to have a value network, you would do this.
You'll do this, yeah. Somehow, yeah, I think for these text generation tasks, somehow value network isn't super helpful. But if you go back to these old school tasks that we have, right, like these Mujoka's robotic simulators controls, trajectory-wise optimization is really hard. It's really hard to get the humanoid to walk. You can try out things like GRPO. You can try Rebel even. I did try Rebel. It works well for things like swimmer, but for things beyond swimmer, like a humanoid running, it just doesn't work. You can train the humanoid to learn to stand, which is actually pretty good already. But it's really hard to actually let the robot figure out how to take the first step out and start walking from standing. So I think in that stage, you really need some sort of Q functions that can help you to do more fine-grained credit assignment, right? You can't really rely on chances in the rollouts in order to figure out what to do in order to start running or start walking. That seems quite challenging. But for language models, for text generations, optimizing at the trajectory level seems fine for now.
What about like multi-turn style problems, maybe?
Yeah, I mean, multi-turn style problems, I agree. Maybe if you want to do like multiple rounds of interaction between agents and humans, then maybe you have to train some value functions. I'm not sure. But even for these reasoning models, these days, the generation consists of chain of thoughts plus the solutions, right? These generations are pretty long, but I guess people just treat this whole thing, COT plus the response together as a big action and just to reinforce, for instance, right? Or GRPO, right? And they don't train value functions either.
I see.
My personal guess is that whatever the reasoning behavior that we get, whatever the aha moment that they set in the paper, these are probably maybe just corresponding to the moment of a humanoid standing. That's what I feel right now. So we actually haven't get to the stage of humanoid work in language reasoning yet, right? We're just solving like high school math problems. You don't need too much crazy reasoning. You just some aha moment, some reflection, some backtracking is good enough, right? That corresponding to train RL to let humanoid stand, which is pretty good. And this aha moment is actually, I think is, they're not too complicated actually, right? We're just solving math problems. We're just solving high school math problems. And maybe if we really want to solve, math Olympiad problems, get gold medals, we have to do more smart search, right? We can't just do policy gradient on the entire generation, right? At least that's not what DeepMind did, right? They had to do crazy search. They have to do crazy Monte Carlo tree search in the lean space in order to get silver medal level for math Olympiad problems.
Maybe
Yeah, but yeah.
Actually, finish your point.
Oh yeah, I guess my point is that maybe if for really hard problems, right, we really need better reinforcement learning algorithms, but there's a trade-off, right? And how many of us really need to solve international math Olympiad every day, right? I don't need to do that, for instance, right? So maybe those trajectory-wise style optimization methods like GRPO, they are good enough for general population for a lot of tasks that we care about. But for really, really hard problems that requires crazy amount of exploration, being crazy creative, then we may need a better algorithm still, or we needed to do more search.
Could you maybe a bit more explicitly say how we could try to do something like this for like a multi-turn dialogue setting? We talked a little bit about how we could do this for like basically single shot. I generate some text, but let's say it's a person in the loop and I want to actually engage them in a longer conversation.
Right. So I think we can just look at this format that we have, right? So we can think about this multi-turn interaction as an MDP where, let's see, the action is modeling one turn, right? And state S is just the concatenation of the prompt and the conversation that you have so far. The action A is just the next turn's response from the agent, right? And the transition is just, given the current conversation, given the response that the agent provided, human going to generate another response. That's the transition. So in that case, transition going to be stochastic. It's not going to be deterministic, right? Because human response maybe in a stochastic way. So in this case, you basically going to operate in this sort of, sort of a hierarchical sense, right? Where the action is a sequence of tokens, but the action corresponding to one turn response. And now you can actually train the Q functions, right? So Q function sort of modeling, how good, given the partial conversation that I have, given the next turn that the agent generated, how good the whole future conversation would it be? And then you can use this Q function to construct this regression target and optimize your policy for this turn. Right? We did something similar for a follow-up paper, which is basically running something similar, but instead of using training a Q function, we just do rollouts. Right? So we just approximate QSA by resetting to state S, try action A, and then roll out, right, to get an unbiased estimate of the Q. And then we did this for A prime and then roll out again, right? So we just take the difference of the two rollouts. That gives me unbiased estimate of the difference of the Q. And then I just optimize my policy using this loss function.
A here is still token.
A here is a sequence of tokens, but represents a response.
Okay.
It's not the entire conversation, right? Let's see, conversation has 5 turns. So then A here is just one turn, but the one turn can be one response, one paragraph.
I see. But there could be a lot of them.
There could be a lot of them, maybe 10 turns or 20 turns, right?
But since you're only sampling, maybe it's okay. Is that the idea?
Oh, you're saying does the action space is extremely large?
Yes.
Sure, but that's the case for the standard RHF as well, right? When we model the whole sentence as an action.
But now you need to learn a function Q that map S from large action space. Like
Correct. Yeah. I guess in this case is maybe regularizing to PyRef really is kind of important, right?
Okay.
And I guess the reason stochastic dynamics are okay here is because they cancel out in the log ratio, right?
Right, right, yeah. Yeah, so that's a good point. Actually, this is something that I pointed out in my class when I asked them to do, the programming assignment on Mujokas, right? So instead of the Mujokas, maybe you have unknown transition. So you can model, the trajectory likelihood, log pi, right, tau given S0, right? So this can be written as sum over, actually, if I do this. So this is written as, the product of policy AH given SH times transition SH plus 1 given SH AH, right? So you can't naively compute the trajectory likelihood anymore if your environment has this stochastic transition, right? And if this P is unknown. But you can still apply this in the DPO or the rebel objective, right? Remember, in that case, is all we care about is the ratio. I owed E given S0, right? And the transition just cancels out, and all you left is sum over H equals 0 to capital H minus 1 log of the corresponding policy one-step policy ratio. Okay, so that's the derivation that you would use if you're trying to apply DPO and rebel to, let's see, OpenAI GM environments, right?
Got it. Or if it's like a stochastic dialogue or something like that, that kind of cancels out.
Yep.
You mentioned one other thing that's kind of interesting here, which was this idea of like doing, I guess like resetting to some state S and then trying out multiple things from it. Have you thought more about how that can be useful for various things in kind of language model fine tuning?
Great. Yeah, so resetting. I guess when we apply the idea of a rebel to like the multi-turn dialogue stuff, we actually do resetting. So by resetting, I mean like this, right? So you can start at a state S, try something, then you come back to state S again and try something out. I guess in general, resetting in these text generation problems, they're free in the sense that, this is not an assumption anymore, right? You can actually just do this. And resetting typically isn't a strong assumption if you want to apply RL to other real-world applications, let's say robotics, for instance. But resetting is kind of free in text generation. You can always do reset. What are the benefits? I guess in general, if you can do reset, right? If you can go back to some places where you sort of were uncertain about what to do and go back to that place and try something out, right? That can help you address things like credit assignment better, right? So you don't have to rely on, random chances so that the next time you do a rollout, you get to the similar state and try something different, right? So it allows you to do credit assignment much easier. You go back to the same place that you were uncertain, try out something different, and then just learn from these two experiences. So resetting is often a game changer in RL. This is true in RL theory for a lot of problems that we know that we cannot solve without resetting, right? But if you are willing to assume resetting to some degree, then you can actually solve them very nicely in RL theory. I think in practice, that's a trick that people use all the time, right? If you know the Monte Carlo tree search, that you're basically doing resetting. So Google uses this for their AlphaGo that beats human champions, right? They do MCTS, so they have to reset all the time. And they do this MCTS search for their Alpha Proof, which got the silver medal in International Mass Olympiad last year. They also do a lot of resetting, right? Basically, when you do MCTS, when you do search, tree search, you kind of have to reset all the time. So they are taking advantage of resetting. What are other good examples of resetting? I guess Goko does a bunch of resetting for his inverse RL stuff, right? And that gives him a theoretically nice algorithm and also a computationally tractable algorithm, something that you can actually apply in real applications.
Yeah, I guess one thing that I'd be curious your thoughts about is like, what is the what's the right reset distribution here, right? Like, I guess for the stuff we talked about in inverse RL, we said, okay, use expert demonstrations, right? Have you thought much about what might be the sort of right, reset, aka the kind of prefix we use for language?
Yeah, I think the question is a little bit I don't know. It's a little bit hard, right? I mean, you have a paper on it, so you know the answer, Gokul. I yeah, I don't know. I think we in this cases we have to talk about things like misspecification and what happens if your policy class is not capable of modeling the expert at all, and then resetting to the expert demonstrations might not be a good idea in that case, right? What kind of resetting distribution we want, what kind of property we need. I think Gokul and I had some paper on this. We had some ideas. We had some thoughts on some of the examples that we created.
Well, I guess I meant it like more practically in the sense that like I could imagine we use maybe like the preferred completions or the dispreferred completions to a prompt or like SFT data or maybe just random internet data or something like this, and all of that could maybe help with exploration in some sense.
Right, sure, yeah. I guess from an exploration perspective, then a diverse data set is always very helpful, right? And you basically want to ensure that the reset distribution covers some good, high quality, optimal policies traces that helps you explore. Yeah. But there are some other sort of issues there, right? I guess we need to talk about things like policy completeness and whatever. It's complicated actually.
Yeah, no, that makes sense. Maybe to close this out, are there any things you're sort of most excited about in kind of RLHF and algorithms for it these days?
Yeah, so we are spending a lot of time in our group working on math reasoning problems, and we had this one paper, Q-sharp, that came out, which I really like a lot. Fortunately, I didn't get a chance to talk about this today. I think in these reasoning tasks, when you have this long COTs, right, it's really important to sort of figure out when you made a mistake, and then make sure your policy knows that it can discover that mistake and then learns how to recover from that mistake. So if you can train such kind of policy in some way, that would be super useful, right? And we provide this Q-sharp algorithm, which we think is a good thing. It has good this kind of sort of recovery behavior. Yeah, so these are basically the things that we care about these days. Trying to learn policies that can recover from mistakes when doing very long, chain of thoughts reasoning for math problems.
Got it. So if I remember Q-sharp, right, it looks something like the kind of aggravate style algorithm
Right.
we had talked
Right.
about in class.
Yeah.
Could you maybe
Yeah.
describe it in terms of that?
Right, so it is similar to aggravate, but remember you don't really have an expert in this case, right? So what we are taking advantage is the closed form solution of the KO regularized RO objective when the transition is deterministic. So in that case is you have a very nice form of the Q optimal Q function or the optimal V function. And we take advantage of that form and train an estimator to estimate Q star for the Q function, the optimal Q function. And then we use that Q function as a guidance to guide the pi-ref, the reference policy in inference time.
Got it. So you can basically kind of get an expert via doing this sort of Q function guidance. And I guess this
Right.
also kind of relates to some of the stuff you've been talking about earlier, about how maybe you can think about using your own base policy with some sort of best event thing as maybe a local expert in some sense.
Right. Yeah, so you can do best of the N as your local experts as well, but that's kind of expensive because you have to do this at the token level. Every token you have to generate N responses. Things quickly becomes intractable. So we don't do multiple routes. We just take advantage of, I guess I can write this here. So maybe, we know that for KO regularized RL, the optimal V star, S, right? It looks like, expectation of tau from pi given S, and exp of reward of S plus tau for beta. That is exp. Right, so in other words, the optimal value function, if you exponentiate the optimal value function, and this is actually equals to the expected value, the expected exponential reward on trajectories generated from pi-ref. So you just start from S, you roll out a trajectory tau, you exponentiate, you take expectation of this random variable, that gives you the exponential value of the V star. right? In other words, the V star here only depends on the rod from PyRef, right? You don't need to worry too much about the dynamic programming, for instance, in this case, for deterministic transition. That means that you can kind of train a V star. You can kind of train this whole thing, right? By just doing regression to this guy.
Got it. So we have R here, and we're gonna train V star via sort of critic fitting kind of regression style things. Got it. That makes sense.
Right. And once you get that, you can just do guidance, right? It's PyRef, multiply exp of V star S plus the next action A over eta, right? So this is your IAS, right?
And by guidance here, we mean basically looking at the logics from PyRef and adding in the.
Correct. This guy.
Got it. Okay. Cool. All right. Well, I think we're at time. So thank you for the lecture, Wen, and thank you for answering many questions. And yeah.
Yeah, it was fun. All right. Okay.
Thanks.
See you guys.
Bye.